get going. I'm going to blather for a little while and the last few people can straggle in and just catch the talk as it gets started. So I want to say welcome to everyone. Thank you for joining us today for this next installment in the Aurora Research Institute virtual speaker series. My name is Annika Trimble. I'm the outreach coordinator for ARI, or Aurora Research Institute. I'm based in Inuvik. It's wonderful to see everyone gathered here today from across the NWT and the rest of Canada. So I want to acknowledge that we in Inuvik are on the traditional lands of the Gwich'in and the Inuvialuit people. We extend our deepest respect and appreciation for sharing this land with us. And we further extend our respect to all the First Nations, Inuit and Métis people of the North who call this territory home. So before we get started, I just want to go over a few housekeeping things so everyone's aware how they can participate. Anytime during the webinar, if you have a question, you can either put it into the chat, or if you're using the Zoom app, you can put it into the Q&A setting. So if you hover your mouse or your pointer over the main Zoom screen, you'll see a control panel pop up from the bottom, and there should be a little Q&A icon there that you can click on. We're going to wait till the very end to answer all the questions, and we'll just go through them as many as time allows. And for everyone, just to be really clear, we're recording the webinar and we'll post the recording on our speaker series website afterwards. So towards the end of the chat, I'll put the link in there so that people who have joined us will be able to check that out. So this talk, usually we focus on NWT research and findings and efforts and discoveries and innovations. This one is a little bit different. It was made possible by the Canadian Astronomical Society through their Casca Westar Lectureship Program. So the goal of that program is really to bring highlights of current astronomical research to the general public and to students, and they do that with the help of Canadian professional astronomers. So the program is primarily about sponsoring visits by those astronomers to schools and to communities that don't have easy access to nearby, like universities or institutions that have space programs and facilities. So we got approved under this program to have someone come to the North and tour around and visit some schools and do some public talks. And then guess what happened? I don't need to say it out loud. Anyway, so we've kind of taken some time to wait, but now decide finally, let's do this virtually. So we're really pleased because it actually lets us share this special opportunity with more people in the North and to a lot of classrooms as well in the NWT. So without any further ado, I want to introduce our speaker today, Stanimir or Stan Metchev. He's a professor of astronomy and a researcher from Western University, which is in Ontario. He'll be talking today about weather on other worlds. I got a preview yesterday. It's very cool stuff and mind-boggling. So I hope you enjoy the presentation. Yeah, and Stan, you're free to take it away.
Thank you, Annika. Thank you for this very kind introduction and for the very kind invitation to present at ARI. I really wish I could have been there in person. In fact, 2 years ago, as part of the same series, I did visit Igloolik in Nunavut. I spent a week there in Igloolik and visited all the schools and met all the students, and that was an unforgettable experience. I do hope that I'll get an opportunity to visit Inuvik as well. And before I continue, I would like to also acknowledge, in fact, as a new citizen of Canada, just as of 2 weeks ago, I am very privileged to live on the traditional grounds of the First Nations of the Anishinaabe, the Haudenosaunee, the Lenape, and the Arawandron peoples, which is also where Western University is located. And my research, as Annika indicated, actually has to deal with other worlds outside the solar system, and the kinds of stuff that we do in my team at Western University is actually study the atmospheres and, believe it or not, even the weather patterns on other planets. And hopefully by the end of this, you'll actually also see if there's a reason for us to care about this. So let's take a little bit of a bigger picture view of where we are now in astronomy in the search for other planets around other stars. as of yesterday, and I don't think the number has changed today, we know over 4,700 extrasolar planets or exoplanets. And you can see here how the number of the known planets has been growing. I believe you can see my cursor has been growing since the discovery of the first one in 1995 to nowadays, over 20 years later, where we know close to 5,000. And some of these are several planets per star. So in fact, there's somewhat fewer planetary systems known. And indeed, at this point, we already know a planetary system with 8 planets, another planetary system with 8 planets like the sun. So now what is really becoming interesting is to find the planets that may host life or aliens. So the kinds of planets that we're looking for now are in the so-called habitable zone around their host stars. So the Earth, by definition, is in the habitable zone. And the kind of planet we're looking for is one that is not too hot, not too cold, is about the size of the Earth. And so the temperature and maybe even the atmospheric conditions on the planet are such that the planet could sustain water in liquid form on its surface, which is necessary for life as we know it. We know that life on Earth requires water everywhere. This is actually an aerial shot of Inuvik on the banks of the Mackenzie River. So you can see water is essential for a settlement anywhere. It's essential even when it is not summer. So this is a picture that I took from the Inuvik website. Shows winter activities. And again, everything is happening on the ice and the snow. So we're looking for planets that would be, again, probably offering similar conditions to what we can have on Earth in the solar system. So some of the ones that have been discovered so far are shown here as examples in this artist concept. So these are not actual pictures of the planets and their stars. These are renditions of graphic artists of what these planets may look like. So here's Earth around our sun. Clearly, the sun is much bigger than the Earth, but this is not shown to scale here. And there's a few other examples shown. And this one here in particular, Kepler 186f, as the name of the planet, discovered 7 years ago, was in fact the first Earth-sized extrasolar planet found to orbit in the habitable zone around another star. So this is a pretty similar planet to what we would hope to find as a potentially habitable planet. And this search for habitable planets and the imagination that we can have now about what life can be on them has spurred this a new public outreach push in NASA, where they now are actually producing these exoplanet travel posters. This is all science fiction, of course, at this point, but here's the poster for Kepler 186f. And now, so there's 2 astronauts here in spacesuits next to a fictitious fence and a red forest on the other side. And it's thought that if there is vegetation on this planet, it would actually be colored red because the host star itself is dimmer and redder than our own sun. So the vegetation would have actually adopted to the red light coming from the star. So the motto for this particular planet is where the grass is always redder on the other side. And if you want to see some more of these posters, you can actually go to NASA's Exoplanet Travel Bureau website, and you can see the link at the top, and you click on Explore the Galaxy, and you'll find a few other fascinating graphics of foreign worlds. So let's come back to our picture of, or graph, I should say, of all the known planets. So we know nearly 5,000, and among these now, we know about 60 that are actually potentially habitable. So these, one could argue, are the most exciting planets that we have discovered so far. And we would really like to be able to point our most powerful telescope at them and study them in as much detail and maybe even detect the signatures of life. Now, however, we face a huge problem in trying to do that. Planets are so faint and their stars are so bright that even when we point powerful telescopes like the Hubble Space Telescope, the best that we can hope to see is this big blob, which is all just starlight. This is one of the cameras. This is an image of a nearby star called HR 8799. That's the name of the star. That is now known to host a planetary system. And after very careful reduction of the data, so working with the image to remove the starlight, we actually come out with these 3 blobs here. And these are 3 actual planets around the star. It actually so happens that this star, HR 8799, was the first planetary system to be imaged directly with a telescope. And this was back in 2008. And you can see now 3 planets, but you can see how much fainter they are than the star itself. And there's been a considerable amount of computer graphics work here done to actually make the planets stand out. Oh, and by the way, these planets are not like the Earth at all. They're actually much bigger and much brighter than Jupiter in our solar system. So even if we wanted to see something much smaller than Jupiter, it would be impossible, even with the Hubble Space Telescope. So here's, for example, how this particular system, HR 8799, compares to our own solar system in size. And this is now the size here of Neptune's orbit in the solar system. So you can see this planetary system is actually bigger than the size of our own solar system. And it's actually a 4th planet that we know of now. It's even closer to the star. It's called HR 8799e. And next, I actually have a better comparison of the 2 planetary systems, HR 8799, with the 3 outer planets. They're all giant planets, like Jupiter or bigger, and our own solar system, which has Jupiter close in here, Saturn, Uranus, Neptune. Of course, what is not shown in this figure are the terrestrial planets, Earth and Mars and Venus and Mercury, which are all much closer to the sun. They're actually basically within the size of this yellow dot here, which is the size of the sun, which is the location of the sun. But you see, there's no hope for us, at least for now, to be able to see something this close to a star when we have to contend with this kind of light in our telescopes. So even though we know of almost 5,000 planets, we have actually managed to see directly very, very few, fewer than the ones that actually even thought to be potentially habitable. About a dozen planets around the stars have been imaged directly. So if we're looking for life elsewhere, what are we to do now? Do we have to wait for a century before technology improves to the point where we can actually start studying habitable planets in any sort of detail? And the answer is maybe partially yes, but we can prepare a lot for that time by solving some other problems in astronomy first. And there's an easier problem to solve. We can actually study very easily the atmospheres of these objects called brown dwarfs. And this is here an artist picture again of what a brown dwarf may look like compared to Jupiter in the solar system. Here's Earth, this much smaller than Jupiter. Here's a brown dwarf, and here's a very low mass star, maybe a little bit bigger than a brown dwarf, and then here's a sun for a comparison. These brown dwarfs are actually quite fascinating if we want to study planets. They kind of fall in between what planets are and what stars are. And here's a distinctive feature. Stars fuse hydrogen atoms in their cores, and that's how they produce light. Brown dwarfs do not have enough mass. They're less massive than a star. So the smallest star is about 80 times the mass of Jupiter, the planet Jupiter in our own solar system. A brown dwarf is somewhere in between, and planets can go up to about 10 to 13 times Jupiter's mass. So a brown dwarf cannot shine with its own light, kind of like a star, but it's not exactly like a planet either because it did not form around a star itself. So it's really, in some sense, a wannabe star. It never just had enough mass to become a star. But because it's not that hot, not as luminous, it actually will have very much an atmosphere like a planet, like a giant planet does. An atmosphere with clouds, with storms, with trade winds. And in that sense, they're very similar to planets. And they, because they're more massive, they also actually happen to be somewhat brighter than planets too. So brown dwarfs, like planets, have atmospheres, clouds and storms. They're hotter and brighter than planets, which makes them easier to observe than planets. And they also roam on their own generally. So they don't have a bright star next to them. So we don't have to contend with this much light coming from a star when we want to observe the atmosphere of something that looks like a planet. So in my team, we have chosen actually to look at brown dwarfs because that will allow us to develop the same methods that we want to use in the future to study planets around other stars. So let's take a look at Jupiter. This is a video, I guess a collection of images of Jupiter as it is rotating around its axis. Jupiter in our solar system. And I use Jupiter often to explain what brown dwarfs may actually look like. Because brown dwarfs are about the same size as Jupiter, turns out, and they kind of have similar atmospheres too. So they're kind of like planets. If we look at Jupiter, this is an animation of Jupiter seen at visible light. You can see now these bands of different colors, and these spots that you see here are storms. They're very large storms. Here's a great red spot, which is the biggest storm in the solar system. So you see all these clouds and storms. If you look at it at a different wavelength of light, at infrared wavelength, about 10 times longer wavelength than visible light, then you can actually see now that different parts of it have different brightness. And the ones that are brighter, you're actually looking deeper in the atmosphere of the planet. So you're seeing a much hotter region of the atmosphere of the planet. And where it's cooler, you're actually seeing something that's higher up in the atmosphere and it looks less bright. So you're actually seeing light coming from the interior of the planet in this case, whereas here on the left at visible light, you're seeing light reflected from the clouds. It's sunlight reflected by the clouds. So now let's compare Jupiter to what we think we now know about brown dwarfs. Here is another animation of a brown dwarf, and this is not a resolved picture of a brown dwarf. Again, this is what a graphics artist has produced based on what we think is happening on a brown dwarf. Again, seen maybe at the same infrared light as we observe Jupiter in this picture. And you can see the same kinds of things in the atmosphere here, a big storm, these trade winds going, or jet stream winds, if you will, going in one way in one hemisphere and the opposite way in the other hemisphere. And you can actually see they're not uniform in brightness. And this actually, this difference in brightness that these big bands have on the brown dwarf are the key to us being able to detect them in the first place. So what can we do to actually figure out that brown dwarfs have these kinds of atmospheres and clouds and storms when we cannot actually see their surfaces at all? They're sufficiently far that all they look like, even in our most powerful telescopes, are little points of light. So what we do is, instead of trying to actually see features on the surface, which we can't, what we can do is observe the brown dwarf over a long period of time. And we did this with one of NASA's space telescopes called the Spitzer Space Telescope, which observed very well at infrared wavelengths. And as we observe a brown dwarf over time, we can actually see how those atmospheric features on the surface, like the storms or those bright bands, will change the brightness of the object as it spins on its own axis, like any planet spins on its own axis. So here's an example of that. This is an observation of a brown dwarf over 6 days here, and you can see how its brightness goes up and down and up and down and up and down. And that's each of those peaks here is actually one spin of the brown dwarf apart. So this is, if you will, this is 1 day on the brown dwarf in between here. And you can see, for a comparison, a star that does not have such storms or clouds on it does not vary. This is what a star would look like at the bottom. So this change in the brightness of the brown dwarf is what gives away the fact that it has these storms that contribute to changing brightness in the atmosphere of the brown dwarf. And this is exactly what actually happens. So we think this is the brown dwarf that we're observing, but really all that we are observing is this a sequence of brightness measurements here. These are taken with the Spitzer Space Telescope, and you can see how it varies in time. And when the two bands here that are bright align, the object is brightest, and when there's nothing, the object is faintest. So we do these observations, and this, based on how large the change in brightness is or how it is distributed over time, we can then figure out what is happening in the actual atmosphere in the brown dwarf and see there are these bright regions here, the trade winds, and there's a hemisphere that's kind of empty. And that's really the only thing that we do. We just observe the brightness over time. And then we compare it to what we know about atmospheres of planets to build the picture of the rotating brown dwarf that we have up here on top. So this is how we actually discover these extrasolar clouds and storms. But what can we tell about what these clouds are made of? And in fact, here's something that we have to keep in mind. Brown dwarfs, because they're more massive than planets, tend to also be hotter. So their atmospheres may look very, very different from what we know the atmospheres of planets look like. So here is a comparison of a brown dwarf with Jupiter again, and you can see the temperature of the brown dwarf is about 1,000 degrees Kelvin, whereas the temperature of Jupiter at the top of the atmosphere is only about 170 degrees Kelvin. And for reference, you see at the bottom, I've shown you that the Earth's average temperature is about 290 degrees Kelvin, so it's warmer than Jupiter. And that corresponds to about 13 degrees centigrade. And I understand that Inuvik today is quite a bit colder than that. Just about 13 degrees outside where I live right now. So Jupiter is colder than the Earth, but a brown dwarf is much, much hotter than the Earth. And so then this will decide what the clouds and the storms in the atmosphere will be made of. So here we're looking at Jupiter again, and you can see these different colors. And these different colors are created by clouds of different chemical composition. So what I'm showing you is a scientific graphic now on the right, and I'll walk you through it. What it shows is on the vertical scale, here it shows you altitude above the cloud tops, and 0 being the cloud top, negative meaning you're below the cloud top, positive meaning you're above the cloud top. And you can see three layers of clouds here. One is actually made by water, which is what we have on Earth, and another one is called ammonium hydrosulfide, a little bit higher up, and then there's an ammonium cloud even higher up, and then the cloud is over here. And on the x-axis, on the horizontal axis, you actually have temperature in Kelvin, and again, about 270 Kelvin is where where water freezes. And that's kind of where you expect also, in fact, water to condense and to form clouds in the atmosphere. And so here's the key thing. There is no surface on the planet Jupiter. It's all atmosphere. It's all gas. So the deeper you go down here, the different kinds of condensation you'll have, different kinds of clouds. And at this level, you get water, where water has the sufficient conditions to condense at about this kind of pressure and this kind of temperature. But higher up, you get a different chemical molecule condensing to form a cloud, and this one is orange, not white. And then there's ammonia even higher up, which forms at an even colder temperature. And this is now about the visible cloud top of Jupiter. And ammonia is what gives the yellow color. The ammonium hydrosulfide is what gives the orange color, and the white color is actually not necessarily water; it's even higher cloud tops. But you look at the temperatures here; these are, a few hundred Kelvin. These are somewhat comparable to what we have on Earth, but much cooler than what we have on a brown dwarf. So when you look at how the clouds on a brown dwarf may be, you have to take into account how hot the object is. So on Jupiter, I just showed you that we have layers of ammonia, ammonia hydrosulfide, and water clouds at the top. But actually, if you go deeper in the atmosphere, and again, Jupiter is all atmosphere, there's no hard surface, you will start getting clouds that are made of fluorides. These are basically salts. And you get these funky sulfide clouds. And then you get deeper and you go look like liquid sand clouds and liquid metal clouds, and then crystal clouds, and so forth. But now, if you're going to a warmer object like a brown dwarf, you don't have these very light clouds that evaporate easily. You actually move this whole stack, this whole layer cake goes up, and you start losing against the the lightest clouds at higher temperatures. And in a brown dwarf, you really, at the cloud tops, you actually have clouds made of liquid sand, liquid silicates, or iron liquid. And these are, so I'm zooming in a little bit here because I want to show you the kinds of material that these correspond to. Here we have salts, so not quite table salt, which is sodium chloride, but again, different kinds of chlorides. So salt clouds in these cold brown dwarfs, but in warmer brown dwarfs, we have liquid or a sand vapor. And this, as a reminder, matter can exist in several phases. So it can be in gas, it can be in liquid, it can be a crystal, it could be plasma. In this case, you have actually clouds that are made of silicates, of sand, or clouds that are made of iron vapor. These are pieces of iron here on Earth, or clouds that are made of oxide crystals. These are oxide crystals here. So very exotic chemistry in these clouds. So now imagine what a storm looks like on one of these objects. You have lightning, but the rain that's falling is maybe iron droplets or maybe sand droplets, and then it's falling into this region of maybe molten iron underneath that's very hot. So it's a very, very hostile environment, very, very exotic. All right, so I mean, this is fun. It's as an astronomer, this is very exciting. But why does it all matter? Especially in the context of us say, when we're looking for life elsewhere. So let's go back to our spinning brown dwarf. We inferred this picture of the brown dwarf based only on these observations. So all we did is just measure how the brightness of the object changes over time. And because it is spinning, we see a different side of it all the time, and we can see what different parts of its atmosphere then look like. But the actual reality is that we can apply this same approach to a planet as well. And let's see, let's take a look at our own Earth. And as it spins, you'll see it has regions that have continents, regions that have oceans, so you have storms on it. And this animation here fades the cloud layer away, but it'll repeat itself again. And the truth is that even with the most powerful telescopes, probably in 100 years, we're not going to be able to see any kind of detail on the surface of a planet in the habitable zone around another star. However, we would be able to measure how its brightness changes as this planet spins. And that will tell us then whether we have things like oceans on it or continents and what the ratio of water to land surface is. We may even be able to detect vegetation by how the brightness also changes with the wavelength of light. And let's take this one step further. Let's take a look at the Earth at nighttime. And what you see here is you're actually seeing all the lights from the big cities on Earth. And you would actually be able to potentially measure the combined light of cities of a relatively nearby Earth-like planet. And again, all you have to do is, as that planet spins, measure how its brightness changes. And so here I'm superposing the earlier animation that I had of the brightness of the brown dwarf. So it's not actually made to match the brightness of the Earth spinning at nighttime, but it's exactly the same kind of observation that we want to do to measure what the surfaces of potentially habitable planets might look like. And it will be the telescopes of the next generation that will be helping us to do this. And as you may know, NASA is planning to launch its next big space telescope called the James Webb Space Telescope in just about 6 months on Halloween Day this year. And hopefully that will not get delayed. So this will be an essential tool for us to be able to study potentially habitable planets and brown dwarfs around in other planetary systems. So this is really all I had is the how the study of these exotic objects called brown dwarfs and the very bizarre storms that they have on them actually are leading us toward the exploration of potentially habitable planets in other planetary systems. And should there be, for the students who may be watching, I also wanted to show them a path of how one might actually get involved in astronomy or even in the sciences. So once you finish high school, you can go to university for 4 to 5 years. And if you're interested in sciences, you can actually work with a professor whose research interests you. And for example, I have students approaching me to work in astronomy on planets around other stars or on brown dwarfs. And especially during the summer, you can actually get paid for your work. So this is a full-time job during the summer, so you get a little bit of money for it. And what you learn along the way are not just physics and astronomy, but you also learn very essential skills like computer programming, because all we do nowadays, even when we're using telescopes, is actually looking at images, at data. So we need computers to make sense of all these data. And then if you're interested in to continue working in the sciences, you can go to graduate school, which is you would be continuing in university, but you'll be getting a master's degree, a Master of Science, MSc, which would be 2 years. Or afterwards, if you want to still continue, you'd be getting a doctorate, a PhD, which is about 4 years. And again, this will be actually a full-time job. You get some money for that. So you don't have to pay your way into it. And if at that point you still want to stay in sciences after university, you can start doing your professional training in the sciences. So now you get a fellowship, which actually pays quite a bit more. And you're a true scientist, you're a postdoctoral scientist. So you have finished your doctoral degree, your PhD. And then afterwards, if you want to stay in what we call academia, in the sciences, you can start working at university, or you can start working for companies in industry, or you can start working for the government, or continue working even in the financial sector with the skills that you've acquired, and then you have a very good career. So if you're interested in the sciences, I strongly encourage you to pursue university and post-university studies. And that's all I had for today. I really thank you for having me, and I'm happy to receive questions. I did not want to have this go on for too long.
All right. So I just wanna, let's see here. All right, so thank you so much, Stan. I never knew about brown dwarfs, or that something could be in between a planet and a star before. So that was really fascinating to me, and it's interesting, like what all you can learn about something in space just from the transmission of light. So that's really exciting. We have some questions that have come up. This one was a little bit early in the presentation. It says, how do you know that these 60 planets are potentially habitable if you've only seen a dozen directly?
So that is a very good question. Let's see if I can go back to that, but I don't have a slide that will answer this. When we discover a planet around another star, we know how bright the star is, and we can actually tell how far the planet is from the star. And in the solar system, the closer you are to the sun, the hotter it is. The farther you are, the colder it is. And if you're somewhere where the Earth is, you're in the right spot. So then when we find another planet around another star, and we know how far it is from its own star and how bright its own star is, we can then estimate whether this planet actually would be in the right zone, in the habitable zone around its host star. to say, well, maybe that planet is in fact potentially habitable because it has the right conditions. Well, we can't hear you, Annika.
Sorry, that was my rookie move. I'm out of practice. So thank you for that. And if you guys, while we're answering them, if you have follow-up questions, by all means, you can go ahead and put them in the chat or in the Q&A. The next question is about brown dwarfs themselves. Are brown dwarfs the same thing as dwarf planets? I've heard of dwarf planets before.
Yeah, so dwarf is a very general term in astronomy. We have dwarf stars, dwarf planets, brown dwarfs, red dwarfs, whatnot. So a dwarf, as a brown dwarf, is more like a dwarf star, and the sun actually itself is a dwarf star, and that separates it from giant stars or supergiant stars, for example, like Betelgeuse or Altair or some of the brightest stars in the sky, some of the stars in the Big Dipper constellation. A dwarf planet is something that we have in a solar system that tends to be something like a big asteroid or a very big comet, or Pluto. Pluto is a dwarf planet. So a brown dwarf is much bigger than a dwarf planet. Brown dwarf is more like the size of Jupiter. A dwarf planet is at most as big as Pluto.
Okay, so good, clearing that up. We have a question. I've read about brown dwarfs with temperatures in the range of a cup of coffee. Are the cold brown dwarfs you mentioned in that range, or is that an example of an even colder brown dwarf?
I see the question from Eric. That's I see he's keeping on top of brown dwarf research, which is very impressive. So the brown dwarfs I was discussing were indeed warmer. But indeed, some of the coldest brown dwarfs that have been discovered now are actually, as cold as room temperature, and they will have atmospheres that we think would be very similar to Earth's atmosphere in terms of what their clouds may be, and it's probably actually raining liquid water in those atmospheres as opposed to the liquid metal rain that I was describing here.
Okay. So there are no more questions in the Q&A, but I'm curious, Stan, what led you to this? Did you, when you were a child growing up, were you thinking, gee, I really want to learn about brown dwarfs? Or like what led you to where you are today? How did you get to be a researcher of astronomy and specifically of brown dwarfs and potential weather on other worlds?
Oh, when I was little, that was before even extrasolar planets were discovered. So we didn't even know those things existed. We were just dreaming of them, but it was mostly really just following dreams and doing a lot of math along the way. That I guess kept me on this track. And then when I realized that you can actually go to school and get paid to do astronomy research, I was, sign me up. I want to continue doing this. So that was graduate school. And then over time, your interests follow maybe sometimes what's the newest thing in the field. So brown dwarfs were coming up, they were just being discovered in the early 2000s, which is when I was starting my academic studies after university. So that's what led to that. Sorry, I still can't hear you now.
Wow, I'm off my game today. All right, sorry guys. So we have we have a few questions here. How do we know what the centers of gas giants, so things like Jupiter, how do we know what the centers of those gas giants are like? You mentioned there's no actual surface.
Yeah, well, we don't know. And it's a very good question. So NASA has sent a spaceship called Juno that's orbiting Jupiter nowadays. And just by the way this spaceship actually orbits around Jupiter, we can measure how, using the laws of gravity, we can measure how mass is distributed in the interior of the planet. So then we can tell that what's been possible to figure out is that the interior, there's no hard core, it's very diffuse. So it's a very exotic state of matter that we can't even reproduce in laboratories because the pressures are so high and the temperatures are so high. But it's no doubt the kinds of states of matter that exists in the interiors of planets and probably even brown dwarfs, in fact.
Okay, thank you. So our next question comes from Oliver. He's 7 years old. Oliver says, I have a book about space, and I know that a long time ago they discovered a way to contact aliens. Have people actually been able to get any messages from any of these planets?
Oliver, I really wish that we could do that. We have tried to contact other civilizations by sending radio signals. The problem is that the nearest stars are so far away still that even if we were to wait for a response from any civilizations on them, we would have to actually wait for maybe several tens of years. And the time hasn't passed, and it's quite possible that the messages that we have sent have not even reached any stars that actually have other civilizations on them. But that is not to say there's no civilizations in our galaxy other than ours, and we're certainly looking for them.
All right. Yes, space is immense. There's a follow-up question about habitable planets. Mars is in the habitable zone, isn't it? If so, Mars isn't habitable, but it's in the same zone as Earth. How can you tell the difference?
Yeah, Mars is in the habitable zone. Actually, what's more, I mean, the moon is in the habitable zone, right? But the moon doesn't have an atmosphere. So to be habitable, you have to have an atmosphere that's sufficiently thick so the water doesn't evaporate on the surface. And that's Mars's problem. Mars does not have enough of an atmosphere to actually keep water from evaporating or just disappearing into space from its surface.
Okay, so maybe not habitable to us humans, but some other tiny things like tardigrades or other things.
Possibly,
so,
that would be super exciting.
Yeah. One more question here. Is Jupiter the biggest planet that's ever been discovered, or is there a bigger one? I'm talking about universal, not just in our solar system.
Yeah, so even some of the planets that I showed in the picture, those 3 planets around the star HR 8799 that were imaged directly, they're thought to be bigger than Jupiter. Maybe as much as 10 times more massive than Jupiter. So Jupiter is not the biggest one. There's many other planets that we now know of that are bigger than Jupiter, but not in our solar system.
When you're differentiating between a planet and a brown dwarf, like we understand there's a couple different criteria, but is size that chief differentiating factor? If you find something as big as a brown dwarf, but it's circling a star, then that makes it a planet, I would guess.
Yeah, so the distinction between planets and brown dwarfs is a very loose one. And in fact, they are about the same size. So when I say bigger than Jupiter, what I really should be saying is more massive than Jupiter, because they actually end up being about the same size. And it doesn't make sense to us on Earth that something more massive is not bigger. But what really just means is that these brown dwarfs are quite a bit denser than Jupiter. They're about the same size, but they're just a lot denser than Jupiter. And even the planets that have been found to be more massive than Jupiter, they still tend to be a similar size. They're just denser than Jupiter.
Okay. Oh, I see another question popped up here. All right. Besides the regular 7 planets, are there any other minuscule planets in our solar system?
That's a good question. We don't quite know. So we have the 8 planets, the 4 rocky ones and the 4 giant ones. It's possible that a planet that is yet to be discovered on a much more distant orbit exists. We haven't seen it yet, but it may be there. And there's also all the dwarf planets. So if you call the dwarf planets minuscule planets, then maybe we have lots of those actually. We have one in between Jupiter and Mars. It's called Ceres. It's effectively the biggest asteroid. And then we have a bunch beyond Neptune, of which Pluto is the most famous one, but there's several others that are also about the same size as Pluto and have their own moons and maybe even have their own rings. So it's actually quite a family of dwarf planets that we have in the solar system.
Nice. Okay, final call for questions. I think we're wrapping up. For those of you, I know there's a few classes that are joining us today or watching the recording. So if you do have questions as a class that come up later, you're very welcome to email them our way. You can, I'll put the email address in the chat, but most of you I've emailed anyways directly. And Stan will get a copy of all of them. Be sure to include your student's name, your community, and then we will record the answers and send it your way sometime, next week. So we'll be in touch about that for those of you who follow up with that opportunity. Otherwise, I want to say thank you to everyone for joining us today, and thank you, Stan, for joining us from Ontario. It's been a treat to have you, and such a different topic, and space always boggles my mind. Like, I am very comfortable with the creatures and the settings that are here, that are under our feet or close to us, that we interact with so much in the north. So it's really wonderful to go skyward with our talks and to think beyond even our solar system. So that's quite exciting, and I thank you for what you've shared with us today. So I think we will leave it at that. Yeah, you're very welcome, and we look forward to, we wish you well in your research, and we look forward to hearing from you some more in the future.
I would look forward to that as well. Yeah, thank you.
You bet. Thank you, everyone, and we'll call it a wrap. Take care.
Bye.
Bye.